So our ultimate goal here is to find out what do electrons do in atoms. So the first thing we're going to look at is what our understanding of the atom was when we stopped talking about the structure of the atom. But what we're going to see is that the understanding of where electrons are in atoms has a lot to do with light. And so the first part of this chapter is just talking about, well, what is light? How do we describe it? What are its properties? But at the beginning of the term, we talked about Dalton's view of atoms. He thought they were indivisible. He didn't realize there were parts to them. Then Thomson came along and he said, well, I think there are these negatively charged particles. They thought of them as cathode rays originally. We now call them electrons. And his notion was that the rest of the atom was kind of like a silly putty that we had these little beads of negative particles in. So the positive charge was all spread out. But then Rutherford came along and he said, no, all that positive charge is actually not spread out. It's condensed into a tiny little space we now call a nucleus, and the electrons are on the outside. And that's where we sort of stop discussing what an atom looks like. The problem with this is that we have this sort of lingering question of, well, we've got negative particles on the outside and a positive particle on the inside. Why don't the electrons just go crashing into the nucleus? And so that's where we're picking up our story. And so to explain this, scientists came up with the idea of making an analogy between the attraction of electromagnetic particles, negative and positive, and gravity, which attracts two masses together. So if I have a ball just hovering in the air, and then gravity acts on it, it's going to fall. Okay, but if I have somebody who is holding that ball and throws it sideways, it's still going to fall, but it's not going to go straight down. Okay, it's going to go sideways a little bit. And fall a little bit further. Now notice that I haven't drawn the ground as flat here. I've drawn a little hill. Okay. So what we're going to think of is that, oops, go back here. No. What if we had something that's curved? Well, if I'm standing on the top of a mountain and I throw the ball sideways, it's not just going to land at the same level I'm standing, it's going to land much further down. Well, the Earth is round, right? So now let's think of this as the moon and the Earth. They're attracted to each other. The moon doesn't crash into the Earth because it's traveling sideways, and it's also falling towards the Earth, but by the time it falls enough that it would get to the surface of the Earth, the curve of the Earth has dropped off. Okay, so this is where we have the scenario where the ball just goes past the end of wherever the curvature is. Okay, and so we call that an orbit. So an orbiting object, whether it's a satellite that's man-made or a moon or the Earth going around the sun, basically it's always traveling towards that thing, trying to crash into it, but it's also going sideways. And so it just keeps missing. It's gone too far sideways by the time that it goes towards it. And so we're thinking of the electrons the same way. The electrons, instead of just randomly moving around, they don't go willy-nilly everywhere. They are, in fact, moving on particular paths in circles. And so those circles allow them to not be sucked into the nucleus. Okay? So this was the original explanation that kind of helped them to say, okay, this is why this is going on. Now, as a side note, we're not going to really get into this. There was another problem that arose from this, that electrons, when they move, that creates electricity, and electricity is a form of energy. So if they're radiating energy, they should personally be losing energy, right? Conservation of mass. So there's energy going out into the environment, so they should slow down and crash. And so the guy who came up with the model that looks like this, the solar system model, he just said, well, they don't. That was sort of his hand-waving explanation. They don't. So, we're not going to get into that. If you take a physics class or whatever, you'll get into more details with that. All right, so we call this Bohr's model of the atom. This is probably the one that if you took chemistry in high school, or even if you did like a chemistry unit in a physical science class, you probably looked at this kind of a model where we had these rings. We sometimes call them shells that the electrons sit on. They're sort of the homes for those electrons. And so as part of Bohr's model, and this is where we get connected to light, they said that the electrons have to stay on these rings. They can't be in between. Kind of like I can be on the first floor of this building or the second floor of this building, but I can't be halfway in between. Pretend stairwells buildings. I can't just walk around on the 1.5 floor. The electrons are the same way. They can be on the first ring or the second ring. They can't be in between. They can move between stuff. And the way that they do that is by putting in energy in the form of light. So if light goes in and hits an electron, and it has just the right amount of energy, it will move it to an outer ring. But if it doesn't have enough energy, it's not going to stay partway in between. It's just going to stay in the original ring. It's not going to go in. Right? And if it has too much, it's not going to go on to the next ring, right? It can only be on one of the rings that already exists. And so when we are looking at, let's say if we're looking at the sun through a spectroscope, and we're looking at the lines, so look like a rainbow, and there'll be some dark lines in it. Those dark lines represent places where light has been absorbed. Now you may have heard people talk about, oh, dark colors absorb a lot of light. That's what they're talking about here, is that individual molecules and atoms have the light coming in, the electrons are being promoted to higher energy levels, and that's how they're absorbing that light. And then eventually it gets, changed into heat energy and makes you hot. Now we can also have the opposite happen, which is when something glows. So if I am burning something, and we will do this in lab in a couple of weeks, then I promoted the electron to higher energy, but eventually it has to fall back down. And so light will come out, and we will see that light as that particular energy or wave. So what we want to know is, can we figure out the energy of the light by knowing something about its wavelength and its frequency? Okay, so that's what this first part is going to be about. How do we describe the wave, and how do we calculate? So we're not going to do much at all, not even just right now, with wave versus particle. I'm just going to say it has both properties and give you a few things that you should probably know, but we're not going to go into a whole lot of the whys and hows. We don't really have time for that. But the difference is that a wave is continuous. Like there's not really a beginning or an end of a wave. It goes up and down and up and down and up and down. Particles, I have a discrete countable unit. So waves are kind of like mashed potatoes, and particles are kind of like peas. Okay? I can have an individual pea. I don't go to a restaurant and say, please give me 3 mashed potatoes. So for today and Wednesday, all we're going to look at is the wave nature. We're not going to get into the particle stuff. Okay, so how do we talk about waves? Waves have an amplitude. Now we typically think of waves as looking like this, going up and down. There's another kind of wave called a longitudinal wave, which is like sound waves, where the air gets compressed and pulled apart, but it doesn't really go up and down. But this works fine for talking about light. So how high it goes up or how low it goes down, that is its amplitude. And that is a measure of the intensity of the light, or how bright a light is, you might think of it. And we also might describe how far apart the waves are from one another. So the easiest thing to do is to pick, on this example, we have the trough or the lowest point and the distance between those two. But I could also go to the peaks, the highest points, and do the distance between those two. It should be the same. And technically, I could pick any part of the wave, so long as I pick exactly that same part of the wave on the other side. On the second. Wavelength is represented by the Greek letter lambda, which looks like that upside down Y there. It's a lowercase lambda. And that stands for L, length. And so that's going to be part of an equation you'll see here in just a second. Now, the other thing we might be interested in is not just how big they are or how far apart they are, but how quickly they're going up and down. So if I have a cork sitting on top of one of these waves here, that cork might be lazily going down, up, then down, up, or it might be going up and down. Okay. So light waves tend to move pretty quickly. And so instead of counting how long it takes to go up and down once, we tend to do it in the other direction and say, okay, if I've only got 1 second, how many times is this wave going to go up and down? And that's on the order of quadrillion times. Okay. Probably hundreds of quadrillions times. It's a pretty big number. Really fast waves. Okay, so that's what we call the frequency. And frequency is represented also by a Greek letter. It looks like a V. If you want to write V in your notes, that's fine. It is nu, the Greek letter N. And we measure that in cycles per second. So usually we just say per second. Or sometimes people will say hertz. So if you've heard of a radio station being so many megahertz or so many kilohertz, that's what that's referring to. But other than those particular instances, we normally just refer to it as per second. So frequency is a good measure of the energy. So if you think about it, lazily going up and down very slowly doesn't take much energy. Going up and down really super fast, that takes a lot of energy. Okay, so high frequency means high energy. So we can put these two things together. If I know how far I've gone and I know how quickly I've done it, I can find my speed. And so that would be the speed of light. Turns out all light, regardless of the color, whether it's ultraviolet or infrared, radio waves, gamma rays, all of those are light. They all travel at the same speed. And we call that the speed of light, C. And as far as we've been able to measure thus far, it's the fastest speed anything goes in the universe.
It just melts slow.
Yeah, so in a vacuum, it's going to go super fast. In the air, it goes a tiny bit slower, not enough slower to make a difference to us. If you're a physicist and you're working on very highly tuned things, then yes, it makes a difference. But for our purposes, it's essentially the same thing. Now, if we send that light through water or glass, then it's going to start doing some other things. We'll get into that later. So in order to calculate C, we would do wavelength times frequency, lambda nu. But we already know the speed of that. That's a constant. It's not going to change. So that's not a very interesting question. So usually what we do is we say, well, if I know the frequency, can I get to the wavelength? Or the other way around. If I know the wavelength, can I get to the frequency? So we can rearrange that equation. Okay, let's go ahead and get started here. Some reminders on the board. You have vocab that is due tomorrow. 2 homework assignments have been posted. One is due Friday. That's over Hess's Law. We'll be working with Hess's Law today. One is over calculations with light. We will be working with some of those today and some of those on Friday. Both of those should help you prepare for the quiz on Monday. So the quiz is basically Hess's law and then the stuff that we talk about with light today and tomorrow. So open this. Okay, any questions about those things? Okay, then also, if you are in my lab, there are a couple of you in here, don't forget to fill out the little questionnaire about which lab you're, not which lab, but whether you're coming at 8:15 or at 9:30. Since it's not going to take you the entire time, I'm only going to have half of you come at 8:15 and half come at 9:30. So if you haven't done so, please fill that out. Make sure that I've got people evenly divided, make sure you know when you're supposed to come. I think that covers it. Okay. So we are going to go back to talking about light here. Okay. Okay. Okay, so we talked about on Monday, the different aspects. Come on. Where are you? Different aspects of waves, and light is a wave. So we can talk about length. Length tells us about color. We'll get to more of that in just a second. Frequency, which is how many up and downs per second. And we can put these measurements together into C equals lambda. What is C? Speed of light. And that is constant for all forms of light, all colors, and also all different types of electromagnetic radiation. Technically, it is constant. It makes the approximation that air is pretty close to a vacuum, so it doesn't change. So then, since it's a constant, we're not usually trying to find C. We're usually trying to find either frequency or wavelength. So frequency looks like the letter V, but it's actually the letter nu in Greek. I don't care if you think of it as a V, but so we could solve that for nu. And we're going to take a moment to practice with that. To practice with that. All right, so I can't remember if we got to this slide. What was that? Did we look at this slide at all on Monday? Okay, so with different wavelengths, since they're all going the same speed, you can think of each of these waves as traveling across that distance there in the same amount of time. Then as that wavelength gets shorter, we increase the number of times that the wave goes up and down in that same amount of time, right? So what this tells us is that a higher wavelength or a longer wavelength will be a lower frequency, and a higher frequency will be a lower wavelength. And this also tells us a little bit about colors, because we actually have colors on here. Now the wavelengths of true colors are a lot shorter than these, but our top one is red. And so red of all of the colors that we can see is the longest wave. Okay, so I would like for you to know the order that the colors appear in a rainbow. And so we can look at Roy G. Biv. Okay. If we look at Roy G. Biv, there it appears on the screen. Okay, Roy G. Biv is red, orange, yellow, green, blue, indigo, violet. And we have 7 different colors here. Indigo isn't important chemically as a separate color. It was actually stuck in there for religious reasons. 6 was considered to be sort of an evil number. The number of the beast was 666. 7 was considered to be a perfect number. So back in the day, they said, oh, we can't have just 6 colors. We need to have 7 colors. So they stuck indigo in there, but to have 7 colors. So what I would like to be able to do is to say, which has a longer wavelength, orange or blue? So knowing the order that these appear in and knowing that red is the long end and violet is the short end, you would say orange has the longer wavelength. Or I might say, which has a higher frequency, violet or yellow? So knowing that violet is on this far end with the shorter wavelength, the shorter the wavelength, the higher the frequency, you would say violet is the highest frequency. Okay? So if we compare yellow and violet, violet is the higher frequency. All right, so let's do a couple of calculations. So here is an example with a red laser pointer that we are going to try and determine the frequency. So a couple of things we need to take note of here. This in this chair. Is that the right side? Yes. Okay. We have NM. NM stands for nanometers, and that is 10 to the minus 9th meters. Okay. Oops. Chair's drifting away. Stay still, chair. All right, so we can plug into our calculator 650 times 10 to the negative 9th. Most calculators can handle that just fine. So it's not proper scientific notation, but your calculator can handle it. Even if you do the EXP button or the EE button, it should work fine. But if I wanted to change that to proper scientific notation, I'd need to move this decimal over 2 spaces. So then the question becomes, well, if I move the decimal by 2, what does my exponent become? Does it go up to negative 11 or does it go down to negative 7? And is it really up and down since negative 11 is shorter and negative 7 is larger? How does it work? I just memorized it. I work with these enough. I know that I'm going to 10 to the minus 7. But if you're not sure, you can plug this into your calculator, 650 nanometers. And then we've got our unit analysis here. Divide by 1 nanometer, so these cancel, and multiply by 10 to the negative 9. And it will tell you that that is, in fact, 6.5 times 10 to the minus 7. And technically, since I was moving that, and I didn't have a decimal before, this really should just be 6.5. Okay, so that's the first thing, is figuring out the nanometers. Now we're going to go back to that equation from 2 slides ago. C is lambda nu. So we're looking for nu. Nu is C over lambda. C will always be given to you. It's a constant. So it is 2.998 times 10 to the 8th. So I put it on this slide. I have a future slide where I didn't write it down. So it's right here as well. Now this is to 4 sig figs. And we almost never need all 4 sig figs. So if you wanted to short that to 3 sig figs,
This 8 would round this 9 up to a 0, and this becomes a 0, and this becomes a 3, and then this becomes a lot easier to remember. 3 times 10 to the 8. You don't have to memorize it because I will give it to you, but if you're using it a lot, that works just as well as this does. All right, so that's our numerator, our top number. And then our denominator is the 650. So I've written it there as 650 times 10 to the negative 9. Now we have to be careful entering this in our calculator, okay? Because I've got times in the denominator, but since both of those numbers are in the denominator on the bottom, I'm dividing by both of those. So what I really want to do is have parentheses around everything in the denominator so that my calculator knows I'm dividing by that whole number. Now, if you are using the EXP button or the EE button, the parentheses aren't necessary, but they're also not going to hurt. So I would recommend putting parentheses around your denominators every time, just to be sure. Now, if you don't happen to have your calculator with you here today, when you get back to your room tonight, pull out your calculator and try these things, because the way that people usually make mistakes on these is with the scientific notation and the fraction. So make sure you are getting the same numbers that we're getting here. So when I plug these in, I get 4.6 times 10 to the 14th hertz. If you have your calculator, you plug those in, make sure you're getting 4.6 times 10 to the 14th hertz. Right. All right, now we have this hertz here that wasn't there before. So if we're doing our unit analysis, you might be like, well, what the heck, where did this new unit came from? So notice that the meters cancel. There's one on top and one on bottom, and there's seconds left over. So what a hertz is a second when it's on the bottom. So notice that the second is underneath that slash mark. So that means it's actually in the denominator. So a hertz is a per second, okay? So when we say it, rather than saying 4.6 times 10 to the 14th per second, which sounds weird, we would say hertz, but usually when we write it, we just write per second. Sometimes you will see seconds with a power of -1, okay? Just so you are familiar with those notations. So that's written down right here if you want to have that in your note, that a hertz is 1/seconds. All right, so the next slide is going to be one that you are going to figure out and work with your table mates to determine. Oh, before I go on to the next slide, something to keep in mind is that if we're dealing with visible light, it's a pretty narrow bandwidth. There aren't a lot of frequencies, and almost all of those frequencies are going to fit into the 10 to the 14th hertz. So when you're dealing with a color, red, green, blue, you should expect your exponent to be 14. If we're dealing with ultraviolet light, the frequency should go up a little bit, and so it should be 10 to the 15. If you're dealing with infrared, it should go down to 10 to the 13. And those will be most of the things we do. Now, I do have some practice things on Canvas. Canvas doesn't handle scientific notation very well. So because of that, I did a couple of things in radio waves, and radio waves, the frequencies and the wavelengths are more like in the thousands. So we can just type in thousands rather than worry about scientific notation. But for tests and things, I'll probably mostly stick with visible light, where this is going to be typically 10 to the 14. Okay, so the next question. We have a green laser pointer, and it has a wavelength of 520 nanometers. And we want to know what is the frequency of that light. So basically the same question. Remember that C is on the board over here. So figure it out, share with your table mates, see if they got the same thing, and then put on the dry erase board what your response is. Okay, so it looks like everybody got D, which is correct. So remember I said that usually it's gonna be 10 to the 14th. If you're taking a multiple choice test, like the MCAT has a large multiple choice test and a lot of those graduate school things, sometimes if you're kind of short on time, you can sort of make a quick guess without doing the calculation. That's the only one that says 10 to the 14th, so you could guess that one knowing that the others are not in there. Now, I'm more apt to want to see your work, so it's good to know how to multiply them out. But if you know approximately what your answer should be, that should help you eliminate choices on multiple choice. All right, I think, oh, I know what I want to do. We are going to go and look at this, the electromagnetic spectrum. So we talked about there being different kinds of light. The ones that are listed in gray here, when we get to the test, I'm going to expect you to know those in order so that I can ask you which has a longer wavelength, radio waves or X-ray, which has a higher frequency, microwaves or infrared. Okay, so you need to know the order that those appear. Notice that the visible light here, it looks like it's really spread out on the bottom so we can see the colors. But these light gray lines here are showing you that it fits into this really narrow band here. So what we can see is just a very small fraction of all of the electromagnetic spectrum. And then if we look at the top here, the top one says wavelength. That's in nanometers. I don't know why they didn't pick meters instead of nanometers, but we can see that our 10 to the 2 hundreds of nanometers is where the visible is. And it increases going to the left so that radio waves are the longer ones. Okay, and it decreases going to the right so that gamma and X-rays are the tiny. Okay, but the frequency, which is listed at the bottom, is reverse. So we have smaller frequencies in the thousands among the radio waves and larger frequencies 10 to the 20 up by the gamma waves. So wavelength and frequency go in opposite directions. On Friday, we're going to be looking at the energies of these. So energy goes with frequency. So if we think about frequency is how often you're going up and down. If you're going to go up and down a whole bunch, you need to have a lot of energy to do that. And if you're just lazily going up and down, you don't need too much energy. So high frequency is high energy. And all of these are light. So we consider them electromagnetic radiation, but we also call them light. And because of that, they're all going to travel at the speed of light. So the equation that we just did for the laser pointers, that equation works for any one of these. So if we know frequency and energy go together, if we throw wavelength into the mix, wavelength is opposite of frequency. So wavelength is also opposite of energy. So if I have a long wavelength, I'm going to have low energy. And we'll talk more on Friday about what each of these different kinds of radiation do. But if I look at something like an X-ray, that has enough energy to strip an electron out of an atom. And when we looked at the visible light the other day, we said that was enough to kind of move the electron away from the nucleus, but not enough to pull it all the way out. Okay, and so the X-ray is enough energy to pull that electron all the way out. That makes it what we call ionizing radiation. So to ionize something is to give it a charge. So if I take away the electron, what's left behind is positive, right? And the reason why that's important is that makes it dangerous. So if I'm doing this to the cells in my body, then suddenly I've got all of these chemicals that are looking for electrons and wanting to react with one another. And they may be doing reactions that are not helpful to you, that can damage the DNA and lead to cancer, and that can cause cell death and things like that. So this is why we want to protect ourselves from radiation as much as we can. I don't want to get off on a sidetrack.
What they do that these stations to go multiple infrared.
Yes, so, yeah, well, not really. One photon can only interact with one electron,
Yeah.
but it still can be stripped off. They are higher energy. They can, it comes from, like cosmic rays, can give gamma radiation, and that's the main way that we would see that. But we have some medical uses where gamma radiation can also be produced from what's called a PET scan, if you've ever heard of that, PET. And that's where they take a matter and an antimatter electron, crash them together, they completely annihilate each other. No conservation of matter here, they are just gone, and they produce 2 gamma rays. So that might be what you're thinking, is that 2 gamma rays are produced from that annihilation. All right, so we are going to switch gears now.